bright in my eyes.
Oh, you're recording.
Oh,
Yeah, go.
are we ready? Okay.
Oh, it's recording.
All right. Welcome back to Bayes, everybody. So we're in the last 3 lectures of the class. So good to see everybody on Zoom. If you have questions throughout the lecture, feel free to type into the chat box, and of course I'll stick around after class to answer your questions. Good review session last night. I think the current homework is starting to solidify everybody's understanding of Bayes factors, how to compute them. Sierra sent out the derivation for the Bayes factor that we are using for our SSVS algorithm. So if you've missed the details there on how to derive that Bayes factor, we did the integrations for you and posted it. So have a look there. If you're still confused, that Bayes factor is correct that we're playing around with. So all you're doing in that homework is going through each beta in the model selection problem that we're working on, and we're sampling from the posterior distribution for it. So we're sampling its full conditional. In the version of it that I gave you, we did the integration up front, so it would make the Gibbs sampler run a little bit faster. There's other implementations, there's slower implementations, and there's even some quicker implementations out there. So lots of implementations, and sometimes the computational burden can be worth it. So I want to just show you a few things before we carry on. I'm going to recap model select, or just kind of summarize model selection today and wrap it up, because I want to get into some other stuff. I'm going to tell you about mixture sampling today and what the Gibbs sampler looks like for that. So a problem analogous to your homework problem. We haven't had time until now to really discuss it. So I'm going to go fairly quick through a couple topics so that we can see more of the landscape of Bayes and familiarize yourself with more of the landscape of Bayes. If you want to code any of this stuff up, so like this paper I'm going to present to you, if you code it up and send me a 2-page write-up on it, I'll give you 10% midterm credit. For the mixture problem that I'm playing around with, if you want to code up the correct mixture sampler that's associated with your previous homework, we'll look at that problem again, you can code that up and get 10% midterm credit. So this class has turned into a choose your own adventure in a lot of ways. So hopefully you take one of the pathways and are successful. But I think what I'm going to try to convince you of is you've got to really code and implement this stuff to really understand it in full glory. So if you're willing to do that, I would be happy to receive write-ups on everything. Those would all be due at the final. So if you're looking for points, we've got Behrens-Fisher, we've got adding model selection to your current, more model selection procedures to your current homework. So again, I like comparisons. So if you want to compare other model selection techniques that you might be familiar with, you can do that for extra credit as well. Lots of opportunities. What do I expect from all of that? That's usually the question. I expect a write-up that basically shows you understand the problem, a couple graphics that explain what you've done. So if you're running a Gibbs sampler, show me the trace plots, things of that nature. What I really expect is it to look professional and clean, and fairly short. So the expectations are pretty open-ended. Okay, let's carry on. So last time we had a couple technical glitches, and we were studying the Bayesian LASSO. I ran an implementation built into MATLAB on the LASSO. Did we get that code sent out? Okay, so Sierra posted that on Slack. So you can look at it, run those examples. I really like that implementation, but there's also other implementations. And one of your classmates asked if that code was executing the Bayesian LASSO. It's a hard question to answer, so I kind of equivocate on this. You get the same answer as the Bayesian LASSO if you ended up looking at the maximum a posterior estimate. So is it the Bayesian LASSO? I mean, that's more of a philosophical question. You're getting the answer from the Bayesian LASSO, but it's not doing the full-blown Bayesian thing. So in a way it is, but in a way it isn't. So you're not sampling from the full posterior, and maybe that's the question. This paper actually takes you through that, and it's not just optimizing as in the implementation that we ran last time. So this paper is really fascinating. And it basically shows you how to run the Gibbs sampler for LASSO in a Bayesian framework. And so I just want to point out a couple things. So this is the problem. This is LASSO. That's what it is. And we've talked about that. So we have this L2 norm. These are sums of squares at the end of the day. And it's being penalized by an L1 norm. That's absolute value. So this is a quadratic function, and this is an absolute function. And so if you regularized using a square, that would be ridge regression, and we have closed form solutions for that. It's a penalized least squares estimate, if you can think about it that way. And the advantage of using the absolute value instead of the quadratic is that you can actually get exact zeros. So, and that's kind of cool. And so if you run this optimization, you get zeros, and that's sweet. So I kind of like it. So it automatically selects for you. Is it the only way to do things? No, it's not. The whole question is, how many zeros do we want to push out of our model? If we have dense model spaces, then we don't want to push too hard. So if we knew a priori there's lots of variables that explain everything, well, then you don't penalize as hard. And if you thought that I've got a sea of data, lots of covariates, and I know that maybe there's only like 5 of them that are meaningful. So the relationship between y and x should be parsimonious, fairly simple. But I've got a whole bunch of covariates, and I've got to get rid of a whole bunch, and I don't know which ones to get rid of. And so in those cases, you want to push really hard and penalize harder. So how do you actually know how hard to push? If you knew something about the problems you were working on, that might give you some insight. But in general, you don't really know. So then you end up doing something like cross-validation. So in a predictive setting, you might try to figure out, if I'm predicting, which covariates predict well. Now that's different than inference in some sense. So, because we're using a prediction criterion. So lots of criterions you can build into this. There's no answer to the question. So just like hypothesis testing, there's no concise answer. So in hypothesis testing, we're asking questions like, is theta equal to 0? And in model selection, we're asking questions like, is a beta k equal to 0, one of the coefficients? So same question, same setup, but this is kind of the computational approach for dealing with it. So lots of stuff to think about. I don't think we're ever going to get to the bottom of this question. I think it's subjective. So by its own nature, but we can impose criterions and have objectives. And then maybe there's a solution to everything. But finding the right model or the correct model, the true model, that can be really hard. And so in simple cases, like data set 1 that I've given you, on your homework, it's pretty simple. So I bet most of you find really close to the right model. But I can start playing around with how I simulate that data in ways that it makes it much more difficult to recover the model. I'm not sure it's always possible. So we can just do well maybe on average in some sense, and we have to always say what that is. I'm going to carry on here. Here's the prior that a Bayesian would be using if they decided to use the lasso. Now this is a little bit different because they put in an extra scale factor right here. This sigma is playing around. And I've done this analysis without a sigma right there, but they're going to butter this up a little bit and utilize that. And I'll show you what I mean. So they're going to play around with this parameter right here and do something really special with it. And what they do with it is right here. So it turns out this is the Laplace distribution that I showed you in class. And it can be derived as a scale mixture of normals. So they've got this scale mixture of normals going on. You'll notice also that they didn't play around with this parameter here. And so it might be too overloaded, but they do discuss it in this paper. But basically what you're supposed to see is that the Laplace distribution, which we're using as our prior, can be written in terms of this integral. This is a normal distribution right here. So it involves some random variable z, that's the random variable over here, and then I've got this scale parameter floating around. So this is a normal centered at 0. And what we're going to mix it with is this distribution. So just like we were playing around with in a lot of our examples earlier, is we did different sort of mixture representations of distributions. So just to remind you, a Cauchy distribution can be derived from a scale mixture of normals. So what distribution are you mixing with? Well, it's been in our homework over and over again, and so I'll let you remember that it's gamma. So we mix over that. This is a slightly different mixture, but the important point is that a normal mixed with a exponential distribution, so that's exponential, ends up inducing a Laplace distribution. Now that seems like, why would I want to do it? This is way simpler than writing this thing down. So let's go back to the Cauchy example that we've been playing around with over and over and over again, or the t distribution. Remember what we are mixing over is we are mixing over the precision parameter. So we had this thing inverted. And so this is, again, a little bit different. And what we were able to do is come up with a Gibbs sampling procedure where I didn't have to deal with something like a t distribution or a Cauchy distribution. So the likelihood function for Cauchy distribution is the product over a whole bunch of stuff, and you cannot simplify it. A normal distribution can be, the likelihood for a normal distribution is a product over a whole bunch of stuff, and it simplifies in terms of x bar and sigma squared. So it simplifies to a simpler, just two-parameter normal distribution. Cauchys don't do that. And so these distributions are a little bit hard to work with as well. Just like in the Cauchy example, Laplace distributions are hard to play around with. But I can play around with normal distributions and exponential distributions fairly easily. And so instead of writing down this nasty likelihood, we can represent it through two different distributions, and those likelihood functions are easy to work with. So that's kind of the key point. They end up rewriting down, in terms of a hierarchy, our original model. So we've got some model, y's are distributed according to a normal distribution. They put an intercept into everything. And then we've got our traditional x betas. When I write everything down, I usually put the intercept into the x matrix with a column of ones. This is an equivalent way of writing that down. And so, but I think it's a good reminder, if we're playing around with regression models, put your intercepts in there. So if you don't, then you're going to have a problem almost certainly. Now, if your intercept is truly 0, maybe it's okay, but a lot of times we need to estimate it in advance to know that we need to, maybe we don't need an intercept. So I say just put the intercept in. If you end up saying, I don't have enough data to estimate the intercept and all of these covariates, you've got bigger problems. So put your intercept in there. And if you can't manage to deal with it because you're so data light, you'll get more data. So I think it's the solution to that. Sometimes you just have to have information in the data to estimate everything. So what they've done here is they ended up representing the betas as a normal distribution. There's some variances in here, so it's just a diagonal representation. And then they're going to end up letting the diagonals right here vary according to an exponential distribution. So this is an exponential distribution. This is a normal distribution. And what they're going to do is they're going to mix these two things together, inducing the lasso. So we end up getting the Laplace representation for these betas. So on this conditional line, the betas are normally distributed. I've got some scale parameters in there, and I'm going to let those scale parameters vary according to an exponential distribution. That's the lasso. You'll notice that in this representation right here, they did not use the lasso on this variance term right here. So you might not want the lasso everywhere, but on all the betas that are depending on those tals, we want to be able to push those out of the model. So this is the lasso. So it's equivalent. It looks maybe more difficult to look at it hierarchically like this, but what this is really doing is telling you how you actually implement the Gibbs sampler. And so you're going to be posterior sampling the betas, conditional on all this stuff, and then you're going to be sampling those. And you're going to be drawing from that exponential prior. And that's going to end up being the lasso at the end of the day. And so if you click through this hierarchy in a Gibbs sampling framework, you get the lasso. So through a scale mixture interpretation. So what's the advantage again? It's computationally feasible. And so everything is easy to deal with in the Gibbs sampling framework. Now, there's still this question of how do you choose the lasso parameter that we've been playing around with? How do I choose the regularizer? And so somehow we need to update that as well. We have not discussed empirical Bayes yet, but I want to allude to something. So they even mentioned right here, you could do all of this using cross-validation and try to estimate that lasso parameter, and that's what we did in last time's example. So we cross-validated to get it. Very frequentist answer. I kind of like that. So I like it in this case, in this setting, and it's probably what I would do. But they have a built-in routine for figuring out what that parameter is. And it's based off of empirical Bayes. And I'm going to give you 2 lectures on empirical Bayes next week. And I'll allude to what empirical Bayes is, maybe at the end of this lecture, certainly by the beginning next time. But they end up adding this line of code to their Gibbs sampler. So at the end of every iteration where I've updated my betas, I've updated my variances, then I end up plugging everything in to this equation right here. And there's a representation of this, and they walk you through the steps. But it's an empirical Bayesian thing, and I'll tell you about that on Monday and Wednesday. They suggest an initialization in this paper as well. How do you initialize everything? How would you initialize the lasso parameter? And they end up using the least squares solution to do it. So they end up looking at x transpose x inverse, x transpose y. If you ended up having a conjugate prior on there, that's essentially ridge regression. So this is really the ridge estimate that they're plugging in. So they initialize their Gibbs sampler with the ridge estimate. And so now we're combining theory. Maybe we don't like the ridge answer as good as the lasso answer, but it gets you kind of in the ballpark of the lasso answer. And so this, if we initialize well, will lower the amount of time our Gibbs samplers need to burn in. And so this is just a suggestion. I've coded it up before, it works pretty decent. Where do they derive all this from? Where do they get, what are they doing with this? They're trying to optimize basically something that it looks like cross-validation. So that this answer, they claim, is competitive against cross-validation. And it has an advantage that I don't have to break up my data set over and over and over again and then choose a lambda, then plug that thing in. That is computationally extremely expensive to do. And so what you would have to do is pick a lambda, run your Gibbs sampler based off of this hierarchy, let everything burn in for a long time. Once it finally burns in and you've converged your Gibbs sampler, then you see how well that answer works on a holdout data set. And you do it again. So at every cross-validation step, you have to run a big Gibbs sampler. And that's a nightmare. So that's just too much to do sometimes. Saying that, you could do it all in parallel. If you had access to supercomputers or thousands of cores or millions of cores, then you could do that. Because each lambda that you ended up looking at and cross-validating, they're independent of each other. So you're running independent Gibbs samplers. So if you had a lot of computers, you could do that. I like that. So it turns out at places like Virginia Tech, we have access to a lot of supercomputers. And so we actually did do our own comparisons a couple of years ago of the answer that you get using this empirical Bayesian formulation against cross-validation. I think they're a little optimistic in this paper. So in terms of how competitive they really are. Obviously it depends on the data, how they simulate the data. And so I wouldn't say they're exactly the same, but they're in the ballpark of each other. So if you want to code that up and check it out and see the differences between those two things, 10% credit. Or you could just read the paper and keep it in mind for the future. So I'm going to move on from this. I think you should read through it. We've got it up on the website, and I'm also going to be appending another paper for you to look at. So I think in graduate school, we need to start reading papers and implementing those papers. That's the whole thing. If you do that, your PhD will be arriving soon. After a while, you come up with an idea for a problem that's hard to solve, and you'll do terrific work in your future, and they'll be delivering your Nobel soon. So get to work. I wish it was that simple. Okay, I want to look at this paper. I just want to see Sierra's favorites. This is very important in her research. So remember, what our basic setup was when we derived our Bayes factor. And so our Bayes factor for our model selection problem in that SSVS implementation was based off of an alternative prior that was normally distributed. And we know that how we pick that diffusion coefficient, the variance term, makes a big difference on how much we're regularizing the space, how much we're pushing things out of our model. So if I end up taking our alternative prior and taking that variance and making it very, very large, I'm going to push everything out of the model. And we don't want to do that. And so if you make it very, very small, then you're not going to push anything out of the model. And so we want something in between. And how do we pick it? It's a good question. So cross-validating, maybe. So that's one answer. There's other empirical methods that you can use, but Bell Johnson has an interesting solution to this problem. And so he proposes a totally different type of prior, not normal for the alternative, because the normal prior, let's say we centered it at 0 if we were trying to apply this in a model selection framework. So I center everything at 0, and then I just have to choose that parameter, but it's very sensitive. So your method is sensitive to that prior, and you have to make a choice at the end of the day. What we often do is we standardize our data, and we pick it to be 1 or 2, something like that. So we have to bring the data onto a scale that we understand. Instead of trying to figure out the scale of the regularizer, we go the other direction. It turns out that the normal prior also, it comes down really fast. It has exponential tails, and that might not put enough mass out off to the sides of 0. And that's the question that we've been playing around with. How much mass do we use? How much do we put on there? Val wrote a really terrific paper. I think this is 2009, 2010, and it kind of rocked the Bayesian world. And some people don't like it, and some people love it. We happen to be in the camp that we really like this method. If you're not sure which method to use, code them both up and compare them, see how it works. And he did a terrific job of mincing theory and implementation in this paper. So basically deriving some Bayes factor here. So I'm going to show you the prior that he used. It takes a while to get into it, but he ends up proving a whole bunch of stuff before we begin. But I think everything really starts in this part of the paper, non-local alternative prior densities. So there's a lot of discussion of using that normal prior before it gets to this, but this is the meat of the paper right here. And he proposes 2 different types of distributions. Here's one of them. So it might look a little wonky to you, difficult to deal with, but here's one of their distributions. And they have another formulation as well. Here's another prior. So instead of the normal prior, Val Johnson proposes this. So I was reading about this in Andy Gelman's blog, and he was discussing it, and he said, sometimes there's a use for using wacky priors. This is pretty wacky looking. It has some advantages. So I want to show you what those functions actually look like. Val plotted them for us, and he plotted them against the normal distribution. So let's just focus on the normal distribution for a second. If we're trying to estimate some parameter, we'll call it theta, and we're trying to determine if it's zero, we could do that Bayesian thing that we spent a couple weeks talking about. And the real question is, how much diffusion do I put in this direction? How flat do I want this thing to be? The problem with that is, remember our null prior. Our null prior is the point mass at zero. So there's a point mass right here. And it's placing mass on zero, and the alternative prior is placing mass away from zero. So if you want to remove the 0 point right there from your normal prior, that's fine. You can. You'll never sample zero anyway. So probability of that point is zero. So with the normal prior, we're stacking mass also really close to zero. We kind of argued before that we want symmetry. We don't know if it's to the left of zero or to the right, so we want to treat those equally. And the normal distribution does that quite nicely. However, it also places a ton of mass at zero. So all the math that he shows in this paper, which I find to be incredibly fascinating, what he says is that if you use the normal prior, then as a function of the data space, n. So how big is n? So as a function of n, say you've got, if your actual data was simulated from the null hypothesis, so the null was true. As a function of n, for any finite variance term, you can't use the flat prior. So for any finite variance, there's a result that he came up with, and it says that if the null were true, we would support the null exponentially fast as a function of n. So as n increases, the probability of the null goes to 1 exponentially fast. So that's great. Like, I love exponentially fast stuff. And so if the null is true, then this prior induces exponentially fast as a function of n. We're going to infer that the null is true. Here's the rub, that if the alternative were true, so theta was anything but 0, we only support that linearly fast, which is much, much slower. So I'd need a lot more data to reject the null properly if the data was generated from the alternative. So these are not balanced. Now the p-value thing is totally unbalanced. So we can only reject the null. So we don't actually use the alternative to calibrate anything. And so Bayesians are putting probabilities on the alternative and probabilities on the null. And what the p-value thing does in the Neyman-Pearsonian framework is we just reject the null. So, but we don't really consider the alternative except for inducing the tail directions. And so I would say the p-value thing in the Neyman-Pearsonian setup, we have like a infinity fast compared to 0 fast. It's like that lopsided. So, but with the normal prior, while you do get good answers sometimes, it puts a little bit too much mass on the null versus the alternative. And Val wants to correct that. And so what did he do? He ended up saying, well, let's just look at, there's a couple different priors here. So the inverse moment one is the one we're going to look at. So this prior, inverse moment prior, and he's got another suggestion as well. So moment priors here, and then inverse moment priors. Let's look at the inverse moment prior. So the inverse moment prior is this solid line right here. And you want to pay attention to this trough. And so it's putting no mass in this region of the alternative. So they're not stacking mass right on top of the null. They're actually budging a little bit farther out. How far out do you budge? Well, if you standardize your data, maybe you just look at one standard deviation. So it's still a question of how far you want that thing to be, but you can calibrate that. What that ends up showing is that under the inverse normal, or inverse moment prior, this one with this flat trough, we support the null exponentially fast as a function of n, and the alternative we support super linearly. So faster than linearly. I'll let you look it up. So the rates are getting closer to each other. Now there's a little bit of bias towards the null, because that's the question we're entertaining. The p-value, as the name in Pearsonian, is only entertaining that half of the question and not the alternative. So the point is that locally around our hypothesized region, our alternative doesn't stack mass there. And it ends up pushing it farther out. And then he wants the tails to come down a lot slower than the normal prior does. These are Cauchy tails. So they kind of look like a Cauchy distribution. So I've been saying for a long time that I think a good prior to use instead of the normal prior is a Cauchy. And so that tends to work a little bit better. Cauchys always put mass way out there in the tails. And so even a standard Cauchy has mass way out there in the tails. And so just using the standard Cauchy is sometimes a good idea. Val's paper takes this one step further, and he ends up removing the mass. So if I ended up drawing this curve, and I ended up following that line all the way through, it looked like a Cauchy distribution. But he's removed a big chunk of it, so down the middle. So he doesn't place a lot of mass on that null. And so because he wants to balance these rates. The disadvantage to using something like a Cauchy prior or this inverse moment prior is computation. So with the Cauchy prior, what we'd need to do is we'd have to do that auxiliary sampler, where I end up using the normal gamma mixture, where we're mixing the precision parameter over a gamma distribution. And that is Cauchy, but I can come up with a good Gibbs implementation to handle that without ever having to deal with the Cauchy. Same thing here. This is even harder to work with computationally. Sierra's like about to cry because it's taken her months to get the thing debugged and all working, but now she's got it. And it's starting to work pretty well. So maybe the effort is worth it sometimes. The nice thing is that more and more every year there's implementations that are fast and free that you can get your hands on. So maybe one of these days we'll have a cool software package where we can just select our different priors and it runs all the different versions of Gibbs samplers for us. That would be sweet. Somebody has to do it and give it to us. So I'm probably not going to do it. Sierra might. So you never know. Anyway, we're just not quite there yet, but there is some code out there for implementing this. So the mathematical result, the theoretical result using this inverse moment prior, I really like. I think it matters, and I think it's possibly even worth all the effort to play around with it. Other people have other opinions. So how do you know which opinion is right? Well, run both versions and do a comparison and see in which settings which method works better, and is it worth the computational cost. For us, it really is. So we work in big high-dimensional spaces and not just one-dimensional spaces. And so placing mass in high-dimensional spaces is even weirder than placing mass in one-dimensional spaces, just because the space is usually empty. And so, anyway, what we do is we come up with a multivariate version of this, and we run our Gibbs samplers. So I just wanted to point out that there's alternatives. So you can't work out the Bayes factor in closed form using this thing. You have to do it computationally. With the normal prior, the advantage is that you can do it all, I can work out the Bayes factor analytically. And that's the PDF that we posted for you, I think, 2 days ago. So, is it worth the burden? I think yes. in the era of a lot of big compute. It's not just big data, but we also have big compute. And so nowadays, everybody has access to thousands of cores. And if you didn't know that, you could go check out something like Amazon Web Services, and they'll give you some trial runs on all of that. And if you like that a whole bunch, we could go over to our friends over at ARC, and they'll give us, gift cards for Amazon Web Services, but they'll also let us use all of their supercomputers. So there's supercomputers everywhere. So if you're at a university in the US, this isn't a burden for most of us. So they bought it, we use it. So I'm just going to move on and just say the Bayes factor can't be computed analytically using the inverse moment prior, but it can be done computationally. So there's that big trade-off. Okay, those are the two papers I wanted to discuss. I want to get into mixture sampling. We'll close down the projector. And I'm going to go back to an example that you're pretty familiar with. So I'll use an example from the homework to illustrate everything. So check. I don't know if we finished model selection. It could go on for years and years and years, but at least we have a foundational understanding of it now. So we're done. Or at least I'm done. I think you guys are still working on your homework. Let's talk about a different problem for a little bit, and I'll show you the Gibbs implementation. So this is a segue, and now we're talking about something completely different. So we're not talking about model selection anymore. I'm going to talk about a different problem. So let me motivate you for a moment. Let's say I have data, and it's generated from this distribution. So what I'm going to say is this right here is some density function. So some density. So in my case, I've got cap K of these densities. So I'm going to say this is the number of mixture components. So number of mixture components. And I'm going to kind of cheap out on this version of the lecture, and I'm going to say this is known. So we're going to assume it's known. Cap K is known. Now, if you didn't know it, I'm going to point you in the direction of something called a Dirichlet process, or you could put some sort of parametric prior on this and try to learn it. So we'd have to put a parametric prior that counts things, because that's a count number. So I think in the old days, people would play around with like Poisson distributions and place a Poisson hierarchy on this. Nowadays, people do something not parametric, semi-parametric, and it's called Dirichlet processes. Just keep that in mind in your notes, so that if you come across a problem and you're thinking, how do I estimate K in the future? Look up Dirichlet processes. Once you start reading through it and you get amply confused, give us a call and we'll try to explain it to you. But let's say this is just some density right here. And then I've got these weights right here. I'm going to call these the mixture weights. So we've been talking about mixtures all through this class. We talked about one today. So it's a scale mixture. But this is different from a scale mixture model. I'm mixing over these different components right here. But they're mixture weights. They're really just probabilities. So these are probabilities of being in that mixture component. So there's some constraints that if they're probabilities, they have to sum to 1. And they need to be positive. I guess technically they could be a 0, but let's say one of them was 0, then we don't have that component in the model. So we'd never actually play around with this in cases where we made that 0. Let me give you a concrete example. You played around with this example in your homework. So you didn't exactly simulate the data out of this thing, but you did something that is the same on average. So let's just think about this. This is a normal distribution right here. So normal densities. So X is normally distributed. It has some mean. I'm going to call that theta. And I'm going to let that theta change for each one of the components. And I'm going to say there's 4 components. So 4 different components in this example. And I'm going to sample 10,000 or 1,000 data points out of this. And so the question is how do you sample from this model? What you did in your homework is you just generated a fixed number of things from each one of the components. But I'm going to think about this in terms of being probability 0.4. The way you did it in your homework when you sampled from this model is you chose 400 data points out of 1,000 that you said would be in component 1. Now I'm saying we want to do this probabilistically. And this is probably what I should have had you do on the homework. We just weren't prepared to talk about this mixture representation yet. So this is 0.4, this is 0.2, 0.3, 0.1. We'll make sure that this sums to 1, so 0.6, 0.9, 1. So that sums to 1. So what we would do to sample from this model is we'd invoke 2 steps. The first step is I would sample K from one of the components. What I'm going to do is I'm going to flip a 4-sided coin and see where it lands. And the sides on the coin are going to have these probabilities on them. So normally I would ask, what distribution is that we're sampling from? This is a multinomial. So multinomials are just like binomials, except there's more cases. So a 2-dimensional multinomial distribution is binomial. So there's only 2 cases. We can extend that concept to any arbitrary number of cases, and that's going to be our number of mixture components. So what we're going to do is we're going to sample this from a multinomial. And I'm going to have my different mixture in here. So I'm going to say down to pi k and keep this a little bit more arbitrary. So I'm going to flip this thing. If I were doing this in this example, I would have this be pi 4 right here. And I would plug those numbers in. So this is just sample from a 4-sided coin, and let's see which side it lands on. So this right here is going to be an element of 1 to cap k. It's going to be one of those numbers. Once I have that number, I'm going to sample from its component. And I'm going to write it down just a little bit more generally. So then I'm going to take xi, and I'm going to sample from fx given theta k. Where this k right here is that k. So in our example, I flip a coin. Let's say it lands on side 3. So then I look at my normal distribution with parameter 17, mean parameter. And I ended up just letting the variance be the same in each one of these. But of course, you can let the variance change in each component as well and try to estimate it. And so at the end of the day, I wind up with data, some number of data points, and it's going to come from some sort of a mixture distribution. So let's just say this is centered at 10. Then I've got something centered at 15. Then I have something centered at 17. Then I have something centered at 20. Now I do understand that I picture variance to be fairly large in all of this, but if I made the variance smaller and we re-simulated the data out of this, I'd have really defined peaks. And this is the data that we would get. So here's our data. Again, how do we generate it? I flip my cap K sided coin with its associated probabilities, and then I generate my data point from that particular mixture component. So that's mixture sampling, and I'm doing it just hierarchically. So it's a two-step process. Flip a coin, then sample from that component. At the end of the day, your XIs are all in here. And this is usually what we get to see. So we observe this. A little bit darker. We observe this stuff. And once we observe that, what we're missing in all of this is we're missing this information. You don't get to see this. Now what I did on the homework is I said generate 400 data points from component 1, generate 200 data points from component 2, 300 data points from component 3, and 100 data points from component 4. So I made these fixed and we didn't do it probabilistically. Now I'm saying, let's just change this a little bit. And let's flip a coin, and on average, I'm gonna get out of 1,000 draws, 400 data points from component 1. So I won't get exactly 400 like you did in the homework, but I'll get something close to it. So what you did is what would happen in expectation. And so now we wanna make it fully stochastic and do this two-step process. The point is that you don't actually get to know what K is behind a particular X. So you see the X, but you don't see the K. If people gave you which data point came from which component, then I would just do our Bayesian, maybe conjugate analysis. If I knew what K was, I knew I had 400 exact points from component 1, and I knew which 400 points there are, I would remove those 400 points from the data set. I would break this into the 4 different distributions. I would assign the K to each X, and I would deal with those 4 inferences independently of each other. Now, if you don't get to see the K, you can't do that, because you don't know where to draw the boundaries and which X came from which K. We really don't know, because these distributions overlap each other. So there's a good amount of overlap in these things. If I showed you an X over here, you'd probably say, ah, it came from component 4. But if I showed you an X in here, you really wouldn't know. And so we need to do something where we infer all of our parameters in our model. In our case, in this example, those are mean parameters for a normal distribution. So I don't think, and I had you play around with this in a hypothesis testing setup, but I don't think that's really the question, is to hypothesize about what the thetas are, but rather you just want to infer them. If I knew what these labels were, then I would infer all of them. Okay, so what I want to show you is how you actually do a Gibbs sampler. When you see data like this, we're going to jointly infer our parameters and what K is for each one of the XIs. How are we doing on time?
110.
110? We're already there.
Yeah.
So I think we'll come back next time then, and we'll look at the Gibbs sampler for all of this. There's just really one line in the Gibbs sampler that I haven't told you about. I think it'll take me about 10 minutes to discuss what that one line in the Gibbs sampler is, and then we're going to move on, turn the page, and I'm going to teach you about empirical Bayes. So this will be a little bit quick, so get an extra strong cup of coffee on Monday, and I'll see you then. Thanks, you guys.